Hello everyone, I hope you're doing well. In this video, we'll calculate the planar density for 111 plane in BCC. Now, this is the most controversial plane for BCC because there were so many people who were asking me that why the central atom in BCC doesn't contribute to the 111 plane and in planar density calculation. Okay, so this is a kind of thing that I didn't answer before and now I'm answering it. So stay tuned, watch this video till end because this video will clarify all your doubts and you'll be so confident in finding out the planar densities and all these calculations. You will not be confused later on anytime. Okay, so let's quickly get started with this planar density calculation for 111 plane. And the first thing that we do in calculating the planar density is to draw the plane. Okay, before drawing it, I just want to mention the formula that we are going to use to calculate the planar density, and it's actually this formula, and that formula applies in every simple cubic or any structure that you are considering, whether it's hexagonal or whatever. So the formula is that it is equals to capital N by A. Planar density is equals to capital N by A, where capital N is net number of atoms centered on the plane divided by the area of the plane. Now the word centered here is really crucial to decide whether the atom is gonna be considered to the plane's property or not. Okay, whether the atom is inside the plane's property or not, that depends whether it's centered on the plane or not. Okay, we'll understand it later on. And divided by the area of the plane. So there are two critical things that we need to calculate. One is capital N and the other is the area of the plane. So symbolically we can write it like that. Let's draw the plane now and see how to calculate these two parameters from that drawn plane. Let's start drawing it. So we have the first square box, then another square box, and I hope you people know how to draw planes when we are given with Miller indices. And 111 plane is such a common plane, we just remember how to draw it. So it has one as x-intercept, one as y-intercept, and one as z-intercept. So this is one on z, and this is one on y. So linking them together through a straight line gives us the plane. Okay, this is the plane, and we can even shade it if we want, but we don't need it exactly because we know we want to calculate some other things. And that is the plane 111 plane, and you can see here that it's in triangular form, and to be specific, it's an equilateral triangle. By equilateral triangle we mean that all the sides of this plane are equal in length. Okay, this is equals to this length and this length, and we can even confirm it. We know that this lattice parameter is a, and this lattice parameter along y is a, and this length is also a. Okay, using the Pythagoras theorem we can find out the length of this hypotenuse. This hypotenuse has the same length, and we can see that this is the triangle here. Okay, it has base a, it has perpendicular a, and hypotenuse is, let's say this length is c, and same cases here. This is the base a, this is the perpendicular a, hence it will also have the similar c side because they have both sides equal. Okay, they have similar sides, so we can calculate this length, as that length will be used to calculate the area. So c is equals to c squared is equals to a square, which is base square, plus a square, which is the perpendicular square. And we can yeah, that is from Pythagoras theorem. We can write that this hypotenuse square equals to base square plus perpendicular square. So c square equals to 2a square, and c is actually equals to, taking under root on both sides, so it's under root 2a. All right, so this is the hypotenuse, and this length, the same length, will be calculated and obtained if we do the calculation for this side and for this side as well. So all these lengths are equal to each other. All right, Now let's see what is the formula that we use to calculate the area of the plane. Area of triangular plane equals 1/2 height into base. All right, and we can see that this is the base of the triangle. Okay, this is the base of the triangle that we already know and we have already calculated, but we need to know the height of the triangle, and we can do so by finding out the length that we have for this point to this center point. Okay, we need to calculate this length, like this vertical length, and this is actually the height of this triangle. So let's do that calculation, and it would be better to denote them by some symbol so that we can refer to them. It's, let's say it's capital A, and let's say this point, this centermost point, is capital B, and we need to know their coordinates because we'll be using the distance formula to calculate the length right away, which is really easy method. And we know the coordinate of this point. Okay, coordinates means how much we have to move along x, y, and z to reach to that point whose coordinates we wanna calculate. So starting from origin, this is origin, I'll move 1 unit along z-axis. 1 unit means to the other corner of the unit cell, and I have reached this point, and I do not need to move along x and y to reach that point. So it's 0 along x, 0 along y, and 1 along z. So that's the coordinates, and this point is at the center of this xy plane. So what I have to do is to move half unit along x and half unit along y, and I have reached this point. So 0 units along z. The coordinates of point B are actually 1/2 along x, 1/2 along y, and 0 along z. So these are the coordinates. Well, okay, now next we need to calculate this AB length, which is actually the height of this triangle. The AB length is actually the height of this triangle, and it is equals to x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square, and it will be multiplied by the lattice parameter because we have the lengths in a unit, so we need to multiply with lattice parameter. And here x2, y2, and z2 are the b coordinates, and x1, y1, and z1 are the a coordinates. Let me write the a coordinates here, which are 0, 0, and 1, and b coordinates are actually 1/2, 1/2, and 0. Let's put value right here to get the height. 1/2 minus 0 whole square, 1/2 minus 0 whole square, 0 minus 1 whole square multiplied by a. Next, 1/2 whole square, 1/2 whole square plus minus 1 whole square into a. It's actually 1/4 plus 1/4 plus 1 into a, and it's 1/2 plus 1 into a, and it's actually under root 3/2 into a. You can find out the LCM, and this is the height. Now we can find out the area of the triangle. Area A equals 1/2 height, which is under root 3/2 into a, into base, which is under root 2 into a. This 2 in the under root and this 2 cancels out, and we have under root 3/2 a squared as the area of the plane. We have successfully calculated the area of the plane right away so easily, and now we need to calculate the net number of atoms lying on the plane. Okay, for net number of atoms lying on the plane, we can see here that obviously we have these corner atoms, and these corner atoms are contributing to the plane. How? Because we can see that the center of corner atoms lie at the corner of the unit cell. We can see here that this is the atom in here, and the atom center is here, and we can see that the plane is cutting through the center of the atom. Whenever you are calculating the planar density, only those atoms are contributing to the plane whose center also lie on the plane. Okay, if atom center is not lying on the plane, then that atom will not be contributed as part of the plane, no matter whether the plane is intersecting the atom or not. Okay, that doesn't matter. The atom's contribution to the plane will be considered only in a case when the plane is also cutting through its center. If it's not cutting through the center, if it's cutting through any other point, then that's not acceptable and that atom will not be contributing to the plane. So we can see here that its center is here and the plane is also passing through this point, so that atom's contribution to the plane will be considered. Similarly, this corner atom will be considered because atom center is at the corner point and the plane is passing through this point. And similarly, we have this atom. We'll see how much of them are contributing. Like we can see, not all the atom, only this much of atom is inside the plane and not all of it. So we'll calculate the contribution of each of these atoms. And other than that, what about the central atom? All right, so the centermost atom is intersected by this plane, but this plane doesn't cut through the center of the atom. Okay, for example, we have this atom here and the plane cuts slightly below the center of the atom. Okay, it doesn't cut actually at the center but slightly below the center. So since the atom is not centered on the plane, okay, it's not centered on the plane, that is why the middle atom is not going to be considered. So how we can know that whether the atom is contributing to the plane or not? What is the mathematical proof or the way to determine it every time when we are confused? So I have attached the proof and method at the end of this video, which is really quick. It only takes 2 minutes to complete the proof, and you can do it even for every atom to see whether this atom is contributing to the plane or not, and that method is really easy. So it is attached to the end. Keep watching. Let me first calculate the planar density. Let me first calculate it, finish it, and then we'll see the proof. But at the end, let me calculate it first and I'll get you the result. And for those who are curious to know how to determine whether the plane is cutting through the center or not, I'll prove it, but at the end. For now, let me proceed with what we have in here. So we can see there that these are the three atoms that are potentially contributing to the plane, and they are centered on the plane as well. This center is a part of this plane, and not all of them is contributing to the plane. So how we are supposed to calculate their contribution? So here what we will do is to find out this angle, which is actually theta. Okay, we'll calculate it right away and we'll compare it to the total angle of the circle, which is 360. We'll find out the ratio. The ratio is actually the contribution of atom to the plane. Okay, and that method works in every situation, whether you're calculating for FCC, SC, or whatever it is. So it's an equilateral triangle. All right, and in equilateral triangle, the total angle of a triangle is 180. Okay, the sum of all the angles is 180, and for an equilateral triangle, equal angle is distributed among each of them, so it's 60 degree. Hence theta equals 60 degree in here. Only in equilateral triangle all of the angles are 60 degree. All right, so this is 60 degree and the total angle of the circle is 360. So the atom's contribution to the plane is 60 divided by 360, which is 1/6. Okay, so 1/6 by this atom, 1/6 by this atom, 1/6 by this atom. So what is the total contribution? Capital N is equals to 3 times 1/6, because there are 3 of atoms, all of them have same, so 3 ones are and 3 twos are, so it's 1/2. That is 1/2. And let's find out the ratio, and let's put the value right here, and 1 1 1. In BCC it's 1/2 as total number of atom divided by under root 3 by 2 and multiply by a square. So this 2 goes up, 2 and 2 cancels out. It's 1 over under root 3 a square as the planar density for 111 plane in BCC. Alright, so this is the formula in terms of lattice parameter, and we can convert it into atomic radius. And for that purpose, we know that the diagonal length is 4r. Since all the diagonal atoms are connected to each other, so this is 1r, this is 2r, and this is another r. So r, 2r, r is 4r. Okay, and this length, what does this length is in terms of a, if you know directly the relationship between atomic radius and the lattice parameter in BCC, you can directly use it, but you can even derive it if you forget it, so you can derive it. So this is the diagonal length, this is length a, and this length is under root 2a. We can easily calculate this length in terms of lattice parameter as well. This is a square plus this is under root 2 a whole square, that is equals to this length, which is actually c square. I'm gonna call it c square or d square. A square plus 2a square equals d square. This is 3a square equals d square, and d is actually under root 3a, and under root 3a equals 4r, and hence a is equals to 4 by under root 3 capital R. So we can put the value right here to get a equals 4 by under root 3r, squaring both sides to get the value of a square. It's 16 by 3 r square. We can put the value right here to get the value of expression of planar density in terms of atomic radius. So it's under root 3. 3 by under root 3 is actually under root 3. You can do this on calculator. And under root 3 by 16 r square. This is the planar density in terms of atomic radius. And this is the atomic density, planar density in terms of lattice parameter, and they have units of atoms per meter square. Okay, whatever results you are going to get, for example, you get 2 multiplied 10 to the power 20, so you are supposed to write atoms per meter square as its unit of planar density. Okay, so or you can write it like that as well, atoms space per meter square. Atoms shows that we have number of atoms right here on the numerator, so this is the planar density of number of atoms. Okay, how much atoms there are on the plane, so that is why we are writing atoms. We can even write it like that as well, but that's more perfect. Okay, that is it for this video. I hope you are clear. Now let's see the evidence or the way we can determine whether the plane is cutting through the center of the atom or not. Okay, let's see how we can do that. Well, now to prove that the plane doesn't pass through the center of this body centered atom, and that is how we can know that whether this atom is centered on this plane or not. Okay, as I told you people earlier, keep that in mind. All those atoms will be considered as putting a contribution to the plane when their centers is also present or intersected by the plane. Okay, and here we can see the centers are intersecting, but we need to know that whether the center atom, which is the body centered atom, its center is exactly at the center of this cube, so whether the plane passes through this center of the cube or not, that is how we can know. If the plane passes through this center point, then it means that the plane passes through the center of this body centered atom as well. But if it doesn't pass through this center of the atom, which is actually the center of this cube, then it means that the plane doesn't intersect through the center of this atom, and hence this center atom is not contributing to this plane. Okay, that is how we can evaluate whether the atom is contributing to the plane or not. All right, so this plane obviously intersects this atom, this body center atom, but not through its center. Okay, but not through its center, and that is why we can say that we the center atom is not contributing. Let's say what is this point? This centermost point is actually 1 by 2 along x, 1 by 2 along y, and 1 by 2 along z. This is the coordinate of the center point, and this is also the coordinate of the center of this body centered atom, because it's body centered atom, it's exactly at the center of the cube. So the point that we want to know, that whether this point lies on the plane or not, that is what we need to inquire. And for that purpose, what you need to do is to use the equation of planes, which is x over a plus y over b plus z over c equals to 1, where a, b, and c are the intercepts of the plane. We know that here we have x-intercept 1, y-intercept is 1 as well, and z-intercept is 1 as well. We can put values for our plane that we are considering. So it's actually x plus y plus z equals to 1, and x, y, and z are actually the points on the plane. Okay, and if this point, this center point, and this center of the atom lies on the plane, then this point will satisfy this equation. And if this point doesn't satisfy this equation, then it means that the point doesn't lie on this plane. Okay, so the left hand side should be equals to the right hand side. That is what we are going to know. This is the right hand side, this is left hand side. So let's calculate the left hand side, which is x plus y plus z, and let's put this point value right here. So 1 by 2 for x, 1 by 2 for y, and 1 by 2 for z. And if you find out the LCM, you will get 1 plus 1 plus 1, which is 3 by 2. And this is not equals to the right hand side, which means that the point 1 by 2, 1 by 2, 1 by 2 that we inserted into this equation doesn't lie on this plane. On this plane with Miller indices 1, 1, 1. All right, so that is how you can inquire whether the point, the center point of the atom lies on the plane or not. Okay, whenever you are confused about whether this atom is contributing to this plane or not, you are confused whether it's yes or not. Okay, so what you have to do in that case, find out the point to inquire which atoms are contributing to the plane. Okay, so you can do this thing, that find the coordinates for the center of the atom, coordinates for the center of the atom, and we did the same. We found the coordinate of the center of the atom, which is actually 1 by 2, 1 by 2, 1 by 2. Okay, the center of body centered atom is at exactly center of the whole cube. That is why we chose this. So first of all, you have to find out the coordinates for the center of the atom, and then what you have to do is to use this equation of planes. All right, this equation of plane, put values of a, b, and c, which are actually the intercepts, which you obviously know because you have successfully drawn the plane inside a cube, and you can't draw it without knowing their intercepts. So intercepts will be given, and you must have calculated it beforehand. So put these intercepts right back in this equation, and put coordinates of center of atom for which you want to have this inquiry. So they will be like x, y, and z here. Okay, so put it here and see whether if right hand side equals left hand side, if the sum is equals to 1, then it means the atom is contributing to the plane, and if right hand side is not equals to left hand side, then it means the atom is not contributing to the plane. Okay, atom is not contributing to the plane. Let me write these rules in neat form, and we will put one other atom into test and see whether we can have this situation or not. Just for your practice, this is true in all the cases, whether it's FCC, BCC, SC, or whatever. Okay, so all right, so here I have mentioned all of the steps that you are supposed to follow. Okay, first of all, find out the coordinates for the center of the atom, and which atom for which you want to run the inquiry. Like you want to see that whether this atom, or this atom, whatever atom you are selecting and you are confused about, you will find out the coordinates for the center of this atom. and after finding out the coordinates you have got the value for x, y, and z. Okay, so they will be x, y, and z values. Now use the equation of planes. This is the equation of planes or surfaces, and it's true for every case. Okay, it's even true for hexagonal, but you have to be you know um, particular about the axis you are selecting, because in hexagonal we have 4 axis lines. So I'll mention that method for hexagonal as well. So put intercepts of planes. Here A is the x-intercept, B is the y-intercept, and C is the z-intercept, and you'll get these intercepts from Miller indices of the plane. Just find out the reciprocal of the Miller indices and you'll get the x, y, and z intercept. And after that, what you have to do is to put these center coordinates, x, y, z values, into this equation as well. Okay, put the intercepts and put the points and see whether the left hand side is equals to right hand side or not. If left hand side is equals to right hand side, then this atom contributes to the plane because its center lie on the plane. If left hand side is not equals to right hand side, it means that the center point of this atom does not lie on the plane, and hence the atom does not contribute to the plane. Okay, keep that in mind. This method only tells you whether this atom contributes to the plane or not. This method doesn't tell you the exact contribution it is making towards the plane. You have to find out the exact contribution by the method of ratio I have told you people, like finding out the theta between the two consecutive lines and dividing it by the total angle of the circle. That gives you the contribution the atom have towards the plane. Okay, that's another story. But for the matter of inquiry, like whether this atom contributes to the plane or not, because sometimes the figures are 3D and we are really confused, just as in the case of body-centered cubic structure. And I was getting a lot of queries about how we can know that and how we can say that. So that's a really quick and easy method that you can use everywhere. Now let's see that whether this atom center lie on the plane or not. We can also inquire about that, and we'll see that the equation will satisfy, and we can know that what is the coordinate of this center point. This is actually the center of the atom as well. We all know that the corner atoms have their center at the corner point, so its coordinates. What are these coordinates? Coordinates are actually the points or the motions that we have to move along x, y, and z in order to reach to that point. So it's like a map. So starting from origin, we'll move 1 unit along x-axis to the other corner of the unit cell, and we have reached this point. So its coordinates are actually 1 and 0, 0, because we don't need to move along y and z. So its coordinates are simply 1, 0, 0. And let's put the value in here. Since we have the same plane in here whose intercepts were 1, so we can put the intercepts here, and we got this equation. Now this is actually the left hand side, so left hand side is equals to x plus y plus z. Let's put the value of the point that we want to inquire. So it's 1, 0, 0, put here, equals to 1. So we can see here that left hand side is equals to the right hand side, which is 1. So this atom, which is located, whose center is located at this point, is contributing to the plane. Again, it is not telling you how much. You have to determine it by the way, but you have confirmed that this atom is contributing to the plane. And you can also inquire whether there is an atom at this corner as well. Its coordinates are 1, 1, and 0. You can easily check out whether this atom is contributing to the plane or not, and you will see that you will get 1 plus 1 plus 0 as x plus y plus z, which is equals to 2, and this is not equals to the right hand side, which was 1. So this atom is not contributing to the plane. See how easy it is. So I'll be doing it for now. Rest of all the videos that I'll be making for the planar density calculation, I'll be remaking all of these videos just to incorporate this stuff as well. So not always the case that you are getting these conventional Miller indices, you will get the tough ones in exam. So I'll be doing it for them so that you may have a complete method to determine it. Okay, so yes, I hope you are crystal clear on how to find out the planar density for any kind of plane that you are given with, so you are never confused now. Okay, first of all, you'll draw the plan. Secondly, you'll find out the area of the plan, and for that purpose you will see what is the shape of this plan. If it's triangular, you'll use the method 1/2 base into height. If it's rectangular, you'll use length into width, and you will use the formula accordingly. And then you have to find out the net number of atoms lying on the plane, centered on the plane. Keep that in mind in case of planes. So for that purpose, you need to know which atoms are actually contributing to the plane before knowing their actual contribution. So for that purpose, you will run that inquiry if you are confused with whether it lies on the plane or not. So you'll run that inquiry. For that purpose, you'll find out the coordinates for the center of each of these atoms, and you'll put those coordinates into the equation of planes equation. You'll see which the atoms which satisfies are actually the ones that are contributing to the plane, and those that doesn't satisfy the equation are the ones that doesn't contribute to the plane. And in that way you have found that which atoms are actually contributing to the plane. And for the calculation of contribution, you'll use this equation. Okay, yeah, let me know if you have any questions still. And I'll also put a similar plane case in description box, which is actually 112 plane in simple cubic, where the similar situation happened and I justified it there as well. So practice it as well.